Okay, so let us start. So we are discussing about the design for additive manufacturing so far, and we have discussed about the DFMA, that is the general DFMA guidelines and the processes behind it. Then we discussed about the unique capabilities of additive manufacturing with respect to the or in comparison with the conventional machining processes. Okay, so these are the various capabilities through which this additive manufacturing can excel when compared to the conventional manufacturing processes. Okay. And we discussed about the shape complexity, hierarchical complexity, functional complexity, and material complexity. Okay. And we discussed about the guidelines for designers which is required. Okay, and also the core DFAM concepts and the objectives. And similarly, we discussed each and every guidelines in detail. Okay, with respect to your complex geometry, your integrated assemblies, how the geometry can be customized, and the multifunctional designs as well. Okay. And finally, we discussed about how to eliminate the conventional DFM constraints when with respect to your additive manufacturing techniques. Okay. And we started off about a small intro about this during the last session, that is exploring design freedoms. So here the design freedoms is nothing but the points wherein it can expand the abilities of a designer. Okay, because whenever you're talking about a conventional manufacturing processes, you will be having design constraints wherein you have the reach or the capability of the machines will be very minimum. And if you want to make two or more operations, you have to go uh, for each and every operation you have to go for a separate machine. Okay, but when you're talking about this additive manufacturing, a single machine is capable of achieving all the processes that could be done collectively by an group of conventional machines. So in that way, you have the freedom to design whatever that is coming to your mind, and you can explore the design freedoms that are available with the additive manufacturing machines. Okay, so that is what they are trying to say. That is, in one approach, you can achieve a significant part consolidation. So here the part consolidation is the main thing, so which is helping you in combining a several parts into a single part. Okay, because I already told you we can build a assembly itself. A complete assembly can be built here. Okay, but that is what in your part consolidation means. And in second approach, you can have hierarchical structures. That is, a single component can exhibit different properties at different locations of the component. So if you're taking a big lengthy scale, okay, you can expect the scales to be very sharp, flexible in the middle, and very tough at the corners. You can tailor make the property, which is not possible in your conventional process. Right. And similarly, in the third approach also, industrial designers explored the application of this additive manufacturing techniques in day-to-day products such as plates, chairs, and clothing. Okay. Now, so let us talk about the collective things, that is part consolidation and redesign. So, here, part consolidation and redesign is nothing but you can consolidate a single part, a group of components into a single part. By that way, you can redesign the entire assembly. Okay, so because you could see here a simple structure which is a component which is used in a diesel engine. Okay, so this is a combination of a variety of parts, small part, that is the assembly. So if you want to print this assembly using a 3D printer, okay, so look at how the design has changed, has evolved. Okay. So when comparing these two designs, you can say for sure the second design has a less material when compared to the first design. So yes, of course, you could say that it has reduced the material to a larger extent. Okay. And similarly, since you are doing it in a single go, you will not be having any fastness. So assembly is completely removed from your production process. So by that way, you can reduce the errors which are occurring due to assembly, and you're reducing the material, and you're of course you're reducing the cost and time through which this particular product has to be manufactured. So a lot more this part consolidation will be giving you the a new design wherein the design will be evolved and will be more efficient than the previous one. That could be taken to the conventional machines. Okay. Next is hierarchical structures. So hierarchical structures is nothing but structures which will be having tailor-made properties. Okay, so if you can fix that this is what your uh, properties, and for that property you can tailor make the materials. Okay, since you are adding the material one by one, you're obviously processing it. Okay, so the processing of the materials will be giving you the required change in material properties. So since you have the process parameters in your hand, so that process parameters can make you to um, alter the properties of the material the way in which it is required. Okay, so that way you can tailor make the properties of your entire structures or the objects which you are manufacturing. So usually the materials will be made in terms of cellular materials. Okay, so cellular materials are the materials with voids. So it will be involving gaps in between. Okay, so like foams or honeycombs, a lattice structure. Okay, so this is a lattice structure. Okay, so if you want to have an square box, okay, you can fill the entire outer portion through an solid material, wherein the inner portion can be filled with these structures called as lattices. Okay, so this will be sufficient enough to withhold the physical integrity of the entire cube, entire box. Okay, so if you want to have an higher force, you can increase the geometry of this lattices such a way that it can easily withstand your entire loads. Okay, so this lattice structures are one of the most type of infills that are being used in most of the 3D printing structures. Okay, especially in your FDM machines. Okay, so this concept of design cellular materials is motivated by the desire to put the material only where it is needed. Okay, for a specific application. So the areas where the material is not required, you can easily avoid the deposition of materials. By that way, you can save a lot of materials. Okay, which will be ultimately reducing your costs and production time. Okay. So from a mechanical engineering point of view, so a key advantage offered by the cellular material is the high strength accompanied by relatively low mass. Yes. So when you're talking about the applications like aerospace, so there you need the materials which are high strength. Obviously, it must be low mass. Okay. So I'm talking about the application that the aerospace. Even in automobiles also the same principle will be applied. So whenever the raw mass is low, the entire efficiency of your a flight or a travel to an automobile will be very much increased. Okay, so but that normally comes in compensation with your weight. Okay, but when you're having a higher strength in a conventional material, the mass will be high. Okay. If you're having a low mass, the strength will be. So that is how a conventional material will be offering. But when you are going for cellular materials, this problem can be easily avoided, and wherein you can get a material which is having a relatively low mass when compared to the same material produced using conventional material and with the high strength. Okay, so obviously strength is one of the major factor which influences the performance of any material. Of course, these thermal and acoustic characteristics as well. So a single material will be having a lot more amount of characteristics that can be built in. Okay, hierarchical structures. So you can design a structure which are being showing you offering you a lot more amount of new areas to be explored. Then is there industrial design application. So whenever talking about industrial design, we are uh, restricting ourselves towards the most conventional designs. But when you're going for this additive manufacturing, for sure you can break that restriction. A good design in your mind, and that cannot be stopped due to your manufacturing process, because this additive manufacturing can try to replicate the same design which is there arising in your mind. So that much amount of capability present in your additive manufacturing techniques. And there are companies which are having freedom of creation, so they were trying to make or fabricate most innovative designs using the additive manufacturing things. They have started in 1996. So look at how earlier they have started. Only few examples I can give you. Innovative designs of gadgets, clothing, even home accessories, even shoes are now being built using that. Okay, so lot more applications are there in industrial point of view as well. So these aspects you can take in, and you can try to explore the more designs and the way in which the additive manufacturing machine can be used. Right. So this gives you the overall structure of additive manufacturing. Okay, starting from like here, and you'll be going for the implicit modeling, so which will be involving uh, all the factors, that is like materials, microstructure, mesostructure, everything. Okay, then you'll be going for process planning, then you'll be going for machining, manufacturing simulator, which will be having taking the control of manufacturing processes, materials, and the mesostructures which you have already decided for. And they'll be having the things to be done, arranging them, and the temperatures, of course, wherein you have to control the flame temperature. So in nutshell, okay, so which shows you the ways in which your data will be flowing through for an DFAM system, right? Now, so being said, so there are a lot of capabilities available with your additive manufacturing, and you can explore a lot of designs. The freedom is with you. How can you do it? Okay, so we'll be finding some of discussing of some of the uh, they have you the applications wherein you can make implementation of additive manufacturing. So when okay, now so the capabilities of AM process have inspired many people here to try design structures so that they have minimum weight without regard to the geometric properties. Okay, so yes, a lot of taking place, they are trying to synthesize lightweight structures. Okay, so why they are more concerned about lightweight structures is nothing, but it offers you a lot more advantage whenever you're talking about lightweight structures. Whenever you're building a structure, right? It is always okay. So there are obviously there is a difference between a metal and a carbon fiber. Yes. So we have heard about lot more about carbon fiber. The major advantage of carbon fiber is it has a higher strength, but it has a low weight. Okay, so that is why most of the higher end applications in aerospace and automotive industries they'll be using carbon fiber. Okay. So similarly, when that usually the carbon fiber is quite costly. So when your machine is offering this particular advantage by the use of the steel powders. If you're using a steel powder, even in a steel powders, if you're getting happening to get a lighter structure, obviously that is one of the major advantage when you're talking about in your application point of views in aerospace and automotive industry. Okay, so even in this lightweight is also good in your electronics and medical applications as well. So that is one of the investigations structured for producing lightweight structures using the additive manufacturing process. Okay. So some recent researchers in this area are they are trying to theoretically obtain optimal lightweight structures, and they are also trying for different optimization methods that they can be applied to get the lightweight structures, and also they are going for topology optimization, basically trying to change the entire product that you are going to produce. Okay. So let us give you a glimpse of what is these. So when you're talking about theoretical lightweight structures, these lightweight structures can be used during the time of everyone would have heard about the term called as trusses. Yeah, truss. So this is what a truss is. So most of you would have seen these trusses in bridges, okay, and to support the roofs in a larger workspace area. So in your rooftops also you'll be good find out trusses. Okay, so now we're talking about trusses. This is the load distribution. So whenever you're talking about the load distribution, this truss will distribute the load equal and can carry more number of loads when you're comparing to the solid structure, and it will be having minimum amount of materials. So this trusses is taken as one of the key principle in order to produce lightweight structures. So this where came into place in 1970s. Okay, there's a man called as Agent Mitchell where he proved the structures can have minimum weight if their members are purely tension compression members, and this try to drive the rules of the process. That is it. This is the tension and the compression. So either they can be pulled or compressed. So this is what the principle of this trusses is. Okay, so this Mitchell trusses layout is now becoming very popular. So you can see some of the uh, draw designs here, wherein you can see. So look at this. This is a rooftop. So the roof is supported by the trusses. So you can see this. So here, this is not a solid structure. Okay, this is just a combination of a lot of links, like what you see in the Eiffel Tower. In Eiffel Tower also, the links only is possible is available there. There is no solid structure. Okay, but it does the work of a solid structure. Okay, so this entire roof is can be supported by the trusses. Obviously, you can also see that there is a very less amount of materials that are being put into. Okay, but the entire structure has been standing still. Okay, so this type of structure is one of the major key principle where developers are trying to represent the entire 100% material structures with a required optimal amount of materials that is only required for withstanding the load. And of course, when you're reducing the material, obviously it will be reducing the cost. So when you're talking about optimization methods, this optimization is used to improve the design. Okay, so just by adjusting the values of design variables in order to achieve the desired objectives. Okay, so usually this will be taking place in terms of structural performances. Okay, so since what I told you here, okay, will be a combination of links. Okay, here this optimization will be can be taking place in terms of what could be the cross section of the links and what could be the thickness of the links. Okay, what could be the shape of the links, what could be the size of the links. Okay, so that kind of optimization will be taking place. Okay, so there are usually three main types of optimization that will be taking place. That is a size optimization, shape optimization, and thickness optimization. Okay, so size optimization is dimensions. Whether if you're talking about the length, so whether it is 100 m, 100 200 mm, or they talking about the diameter, what should be the it should be the 50 mm diameter or 100 diameter. Okay, so that variations in dimensions. Okay, so which dimension will be most optimizable. So obviously, optimization is nothing but the collection of uh, apt variables. Okay, which will be resulting in your desired meeting a desired object. Okay, that is what optimization is. Okay, and similarly, you can also go for shape optimization, wherein you will be changing the material shape and part. Say that this will be suitable. Okay, because when you're talking about shape optimization, the already we have discussed about an example called ear shell. Okay, that is used for hearing aids and okay, so that very useful to you. So you can also refer. Then is your topology optimization. So where the distributions of materials are exported. So here topology is nothing but distribution of materials within a single structure. That is wherever you can distribute more amount of materials at that particular point, and wherever there isn't any load acting, you can also only give the minimal amount number of material. So by optimize the material distribution, which will be ultimately all these optimizations will be ultimately pulling down your costs with respect to all the materials and production processes, and it will be increasing its efficiency, and it will be making it lightweight. Okay? And ultimately, you can have an good profit as well when you're talking about the manufacturing. So let me give you a small glimpse on what is size optimization shape. Your size optimization is nothing but the best typical optimization structure. The objectives could include minimization of stress. So there should not be any stress. If you're talking about, for example, in a larger perspective, if I'm talking about a bridge, it should not deflect. So that kind of optimizations will be your minimize the good strain and should have a very zero deflections and should have a part volume or a good number of weight to volume to weight ratios. Okay, so these will be the optimization objectives. So in order to achieve these objectives, you will be going for the optimization of the parameters. The parameters usually will be the materials and the shape of the materials, the size of the materials, and the topology of the materials. So these will be your optimization. When you're talking about the size optimization here, way smaller dimensions. For example, when you're talking about cellular parts, a small number of size dimensions will be part of the optimization problem. Yeah, so however, for cellular structures such as lattices, these are lattices. Okay, the number of design variables could be the number in terms of tens or hundreds of thousands. So this much large amount of optimizations can be done. Same, you can see the same structure can be optimized through the lattices in this manner and also in this manner. So both is possible. Okay, so here they have optimized the size here. So this is they have given the inner values for a smaller dimensions and the big boxes inside it with the large dimensions. Whereas here they have given the outer boxes with the small dimensions. So depending on the application you are going to choose, you can optimize the size optimization. So in this process here also you can see. So look at how these lattice structures are being optimized depending upon this. If you want to have a flexible type of material, so how you can change the size. Okay, so this way you can optimize the sizes. Then it's shape optimization. So the shape optimization is nothing but it is an size optimization. So whenever you're optimizing the size, of course, the shapes will change. Okay, so typically the shape of a bounded curves or a surface is optimized to achieve similar objectives. So if you're having a very sharp corner, so that will be a very part for a high stress concentration. Always the sharp corners will be the first one to break. So whatever application you take. So whenever there is a sharp corner, for example, if you're having a sharp corner for say a toys or any glasses, so the sharp corner will be the one first to break. Okay. So that shapes can be optimized in order to have the same type of application. Okay. So you can see a lot of examples wherein the shapes are optimized depending upon their application. So this is one of the an architectural object which was done using 3D pen. So if you're talking about Topology, so wherein you are optimized with your hand to build it. So this is for the principle of FDM technology. Okay, so mostly the shapes and size will be of free form shapes. So look at here how free forms are here. So these are all 3D printed using your advanced manufacturing techniques. Topology optimization. So topology optimization is nothing but the overall shape, arrangement of shape elements, and connectivity of the design domain between your various components. Okay, that is what a topology optimization is. So the primary difference between topology optimization and the shape or size optimization are in starting geometry configuration, the choice of variables, which can lead to very significant improvements in the structural performance. So mostly dealing with the configuration and the choice of variables. So related to materials in to be more precise. Okay. So we'll be when we're talking about topology optimization, we'll be playing with the materials and the concentration of the materials. Okay. So topology optimization, a lot of variety of methods are available, which is been now researched, wherein it is used to determine the overall configuration of the shape elements in a design problem. Okay. So topic is in whenever designing the shape, we will be going for the size and shape optimization. Okay. So as a structural optimization methods, finite element analysis is used typically during shape optimization method, which is highly computationally demanding. So I hope you had heard about the term called as finite element analysis. Okay, this finite element analysis is nothing but if you want to analyze a material, whether it can withstand a particular temperature or not, a particular mechanical load or not. Okay, so usually they will be analyzing it. So the analysis is done through the principle of finite element analysis. So most of your mechanical components, electronic components, whatever it is being produced, after designing they'll be put forth for finite element analysis. Okay, simply they'll be calling it as analysis, but it is a finite element analysis. Okay, so wherein we will be creating an virtual environment in which your particular design is going to work. Okay, so it will be a virtual analysis. Okay, and for example, if you're talking about an electronic circuit, so whether the what is the going to be the function environment, working environment for an electrical electronic circuit, whether it is going to work at a lower degree temperature or on a higher elevation. Okay, so you will be creating that environment virtually, and you will be seeing the whether your component design is going to work there in that particular environment or not. So this way we are saying that way going for each and every time going for real time application. So that is one of the areas. So this is a large area. So where I'm just giving you the nutshell what it is. Okay, so that also is one of the most widely performed topology optimization techniques. Okay, so usually there is two main approaches when talking about topology optimization. Okay, one is trust-based methods, and next is a volume-based density method. I'm just going to give you what is a glimpse what it is means. Okay, so trust-based method is nothing but obviously trusses are a combination of struts, okay, different links. Okay, so which will be connected at the nodes. So two or more links will be connected at one particular point. So like this. So we have discussed earlier that when talking about this, each and everything is a stud or a link, and which will be connected at one single particular point. Okay, so this similarly here also this links will be connected to one single node. So this is called as a node. Okay, this is a stud. So when you're talking about this trust-based methods, so is it what would be the volumes of those entire structures? Okay, so what would be the type of mesh we can have it? What type of material we can have it? What type of material we cannot have it? So you will be determining it with the trust-based method. Even you'll be determining what should be the size of the every studs. Okay, so if you are using an circular cylindrical type of stud now, what could be its diameter? Okay, so if there is a particular area where there is a load heavily acting, you can add more number of studs. Okay, and there is any other particular area where there is no load acting in a particular component, you can remove the studs, sir, because there is, whenever you are putting a stud there, it means that you are adding the. Okay. So that is a trust-based method. And when talking about the volume-based density method, so it is just depending upon the amount of material that is being deposited. Okay. So this density-based TO method is most common, and it is used in a commercial software known as simultaneous method is one of the commercial software packages to carry out this topic. Okay. And of course, we do also have two commercial softwares widely used and very popular for topology optimization is OptiStruct, okay, which is given by the Altair, which is one of leading CAE package delivering company. So in that they are having a module called as OptiStruct, which will be helping you to perform topology optimization works. And there is other software called as Abacus, in which we will be having an module called as Atom, like Abacus topology optimization module. which is now being marketed by the Dassault systems. Okay, so both the packages can solve a variety of topology optimization problems. So this is just to give you an glimpse what the synthesis methods are. Okay, this is what your synthesis methods. So this is what I told you. This is a fuselage of an UAV, that is unmanned aerial vehicle. So this is the fuselage. So how to handle if you are not on a unmanned UAV? So it has to be light because it is not going to carry much amount of load, and it should withstand a lot more amount of these stresses. Okay, so when you're going with truss-based method, this is how your truss-based method, the outer structure will be, your fuselage will be looking. Okay. So you can, if you're looking about particular area, so look at here. So in this particular area, this thickness of your links are good, high, whereas in other areas the thickness of the links are low. It means that here is the point wherein the load will be acting. So you can increase the number of, you can increase the size of the studs there, links. Whereas other areas there is, it is not required. So this way you can. There are researches going on wherein you can check. So look at here. This is one of the results of an finite element analysis. Okay, this is a software called as ANSYS, which can offer you this results. Or the one is low and the one is high. It means the difference is with the difference okay, high. So it is good to have more number of struts at that particular point. Okay, so whereas the other areas where there isn't any load acting, where there isn't any stress concentration, so you can go for a minimum level of material deposition. Okay, so this is one of the truss-based methods, and some of the volume-based method is nothing but the one. This is the cargo sling, okay, which is used to transfer the cargo. Okay. So you can see this is one of the design. So you can see this topology optimization variations in the design. Based upon the design and based upon the deflections that is happening, this softwares will be offering you different modified designs, which will be giving you a less number of material that could be used, ultimately giving you an higher hand when compared to the conventional process. Okay. So these topology optimizations are also available with your conventional machines, but this topology optimizations are now being used for additive manufacturing as well. Okay, so this is just a starting area. Only the last 5 years only this processes are going on. Wherein, if you're interested, you can Google it for more information. Okay, so yes, so with this we are going to conclude this session, wherein you observed the opportunities for customizing product performance and cutting manufacturing costs, in general developing new ways to conceptualize products, right? So with this your first half of your unit 5 comes to an end.